Good evening, ladies and gentlemen. How is everybody doing today? I'm also good, thank you. How was your weekend? I'm glad some of your weekends were good. Why was your weekend rough? Okay, I understand. I remember that feeling from in my undergrad working through weekends to get assignments done, study for tests. I know how it feels. How many modules do you guys have this semester? 10, 8, 9, 7. That's a lot of modules. So see, class participation is not that high this evening. There's something happening that I don't know about.
Hi, sir. A lot of people are writing chemistry tomorrow, so
Okay, I understand. Thanks for the info. So again, tonight I'm probably going to preach to the choir, but since last week I've received a few emails asking for help and questions about this subject. But I'm going to ask again for the class, please pay attention to email etiquette. About 70% of emails that are received from the class is in text message styles. Just saying one sentence, hi sir, comma, how do you do this, or what do you mean with that? That's a text message style, and it's not even a new email. It's one of the emails I sent out as a group email that's just been replied to by the class. So if you write an email, please, please, please start it as a new email, have the correct subject. So according to your subject, I prioritize your email. For example, just to give you guys an idea, I do at minimum receive about 80 to 90 emails per day. So if it's really important, really urgent, just write in the subject line, help with something, need information on something, and importance. Then I will know to prioritize your email. So please, guys, remember that. And when you type your email, the body itself, please type an email style, greeting, paragraphs, and please sign off your email with your names, first name, last name, and student number. Otherwise, it becomes more difficult to go first look on a class list. If you provide a student number, if you don't provide a student number, because usually in your TIX emails, I only see your student numbers, who the person is, and who I can help. So please remember that, you guys. And then, secondly, have you guys went through the assignment about Moon? Before we start with tonight's lecture, let's perhaps go through the assignment. Would you guys like that? Okay, so quickly let me just upload the assignment to Blackboard. So while I'm uploading the assignment, is there something interesting in the science world that you guys has learned about, read about in the last week? Anyone would like to share with the class? Yes, the Muon experiment was extremely cool. I think the Muon experiment is a breakthrough for particle physics. It's a new particle that, so when you look at the statistics, there is a 1 in 40,000% chance that this could be a statistical anomaly. Because the chances are so small, it points that this could be it. So this can point to a new force of nature that we haven't discovered yet. And then I saw pictures of blue demons on Mars released by NASA. Yes, those are also pretty cool. Just found out that the scientists believe we are on the verge of discovering a new fifth force. Yes, that's true. That's with the muons. So I'm going to ask you guys, what would be the forces we know so far? Yes, the weak force. What else? Strong nuclear. Yes. Electromagnetism. Yes. Gravity. Yes. So all of those are laws that govern how we understand physics. So there could be now a new one that we don't know about yet, and with muons we can try to understand what's happening. So I'm not a particle physicist, but you will, in your modules for particle physics and quantum mechanics, you will learn more about these forces. So for my career as astronomer, the two most important forces I'm looking at and working with is gravity and electromagnetism. Okay, can everybody see this slide? Okay, so in this assignment, you will have to observe the moon for a minimum period of 10 days. So 10 days will be good enough for the assignment, but if you want to observe longer, you are more than welcome. So the idea is each day when you observe the moon, you have to do it at the exact same time every day or every night for the 10-day period or longer period if you want to. And then you have a piece of paper. You can scan in or take a photo of will be good enough. If you want to make it more fancier by taking pictures, you can do that as well. Astrophotography pictures. If you want to draw it on a computer system, you're more than welcome. I leave it open for interpretation for you as long as I have a sketch of what you observe. So if you observe the moon every day at the exact same time, you will notice that the moon's position has shifted. And that you have to draw on your paper. So you have to have your own scale drawing. to determine this. So if you do the drawing, make sure you are in an area that's not obscuring your view. For example, the moon shifts, so that the path of the moon is not blocked by anything. That's why I'm giving you such a long time to do the assignment, because I know last year a few students made a mistake saying, oh, but I'm on day 8 of my observation and the moon now disappeared below the horizon. What am I supposed to do now? So that is something to keep in mind. I'm just going to share my screen with you to show you this. So if you look in your assignment guide, I suggest, you can do it anytime you want, but I suggest you start your observations on the 20th or 21st of April. So I'm going to share my screen to show you guys why I say this. Let me just share screen. Can everybody see the screen that I'm sharing? So you can Google these times, they are easy. So where we are today, we can see the moon is rising at 6:29 in the morning and the moon sets at 8:21 in the evening. So we can observe the moon in time during the day as long as in between those hours. The reason I suggest we use to start the 20th and 21st of April, if we choose, remember, the moon rise and set will each day move by about 30 to 40 minutes. So you can see on the 20th, the moon rises at 13:26. The following day, it's at 14:11. The following day at 14:53. So you can't choose 1 o'clock. So you have to choose a time where you know the moon will be visible. So for this time period, I would suggest to do your observations from 8 o'clock in the evening. That way we are sure that the moon will be visible and high enough. Then secondly, it also helps with these observations that we have a full moon present. So here we can see is a half moon on the 20th and a full moon will be on the 27th. So I will also give you now I'll share the link with you guys now. So if you click on the next day, it will show you where the moon will be. So here the moon is below the horizon. Here the moon is above the horizon. So let me just share the assignment again. Here is the link from this website. I'm based in Johannesburg. So you can type in your location where you are, but that won't be any different. Different places in the country won't differ that much. Unless you are in Cape Town, then it will only differ. Then it will differ a little bit. So make a scale drawing on your sheet of paper of the landmarks on the horizon as seen from your point of observation. Do this by holding a ruler at arm's length and measuring the height and position of the landmarks and their separation. This can be done in daylight and time before the observations. Work out a convenient scale for this drawing. The same scale will be used to plot the positions of the moon. Measure the position of the center of the moon with respect to your landmarks using the ruler at arm's length. First measure the altitude of the moon, the distance above the horizon, then determine how far east or west the center of the moon is in the sky. Each night, plot the moon's position on your drawing using the scale you use to make the drawing. Use a circular object such as a coin to draw the moon disk on scale. So the moon can be a different scale from a drawing scale. At a plotted position, use shading to draw the phase of the moon as seen in the sky, and note the date and time of the observation on the drawing. Be careful when taking measurements. You may find the length of your measure will be longer than your ruler held at arm's length. When this happens, measure distances in pieces as you would measure anything very long. And then when you've done your observations, there's a few questions you guys need to answer about what you observed. But all of these questions must be answered in the article you are also writing. So the question 1. In the following diagram, 8 positions of the moon are given in its orbit around Earth, labeled 1 through 8. The upper part represents the orbit looking down on it from the north. The lower part illustrates an earthbound observer's view of the moon at each of the 8 positions. For each position, 1 through 8, shade the dark and illuminated portions of the moon from the perspective of an observer above the Earth-Moon system. An observer on the Earth and a lower part. So indicate by using heavy dot or both parts diagram where the moon was at the time of your observations. So let me get a pointer out. So here we are looking from the north. So say for example we are above Earth and the moon. What phases would we be able to see here? And then viewed from the side, which the corresponding image here as well. Then question 2, at what time of the day would you expect to observe a moon rising, a first quarter moon setting, a full moon setting? Then question 3, when you observe a quarter moon, was it first or third quarter, and how can you tell? So you have to explain it. Then 4th, using your crude ruler, measure and estimate the diameter of the moon. Take the moon to be exactly 384,000 kilometers from Earth, so your measurements and calculations. So the technique we are going to use for this, we're going to discuss that in later chapters, but there are a few ways you can determine your so there's a few methods you can do it. If you Google it, you can find it. But one thing to keep in mind, parallax. So, sir, am I correct in saying that we can just take pictures of the moon instead of drawing it? Yes, you are more than welcome to do it, but we need to have clear pictures of the moon and where the position is. Last year, I had a student that took very precise photos of it. So that was also very interesting. I had a guy that painted a portrait of the moon where it will be every night. And there's another person that actually created a device to measure it. So it's all up for you guys. So the assignment is really, really easy. And then the aunt that, yeah, that's perfect. You can use a long lens and put everything in one picture. That's perfect. You're more than welcome to do that if you want to. So it's open for each and every one. So the marking that I'm gonna give for you guys is not how pretty your picture is or how pretty your sketch is. I'm marking you guys based on the scientific knowledge we are getting out of it. Then lastly, I want you guys to write an article. So the article must be, so write a scientific paper of maximum 3 pages describing your observation and explaining your results. Answer the above questions in the scientific paper as well. Please look at article guidelines to help you with your article. So in the scientific world, everything is explained through an article. So here are a few examples you can use. For me, article writing style, more precisely referencing style. Are you guys familiar with referencing? So I personally like the IEEE referencing method. It just works better for me. But you guys are more than welcome to use any reference style you want for referencing. So IEEE stands for Institute for Electrical and Electronic Engineers. You're more than welcome to use the Harvard method or any other method you want to use for referencing. I just like the IEEE, so you see the examples and the style sheet example I provided. I use the IEEE one, but you're more than welcome to use anyone else. So let me just show you a few things with the example to make sure everything is as neat as possible. So in your article, you will always have your heading. Secondly, who you are as persons. So in this example, I gave you your names, initials, name, and student number. And then thirdly, below this, is the institute you are connected to. So in this case, it would be University of Pretoria, Faculty of Natural and Agricultural Sciences, Department of Physics. And that will be in Hatfield, Pretoria, South Africa. And then you have your abstract. The abstract is probably the most difficult part of writing because your abstract needs to summarize your entire article, giving your introduction, what your results are, and what your conclusions is. I would prefer scientific articles, if you guys can please type it out. And then when you start in below your abstract are your keywords. So keywords are usually specific scientific terms. So if a person doesn't know what a keyword means, he knows for fission, isotope, neutrons, that they can quickly go read up about or Google. And then your article is always divided into two columns. So then you can divide it, leave it open to you for what headings you want to use, but your introduction section, nuclear reaction fission section that I write about. Then you go over to your next page. It continues on this way. Your next heading, your conclusion. Always remember you have to have a conclusion in your article. And then your references. And then one thing I want you guys, it's usually not necessary, but it's one thing that irritates me about neatness of articles. You can see here left and right of my writing. This is all in line. 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 There's no gaps in my articles. So the lining from beginning to end of a line is the same length, if that makes sense. And that is the sweet and short. So do you guys have any questions or something you want me to explain? So you have, so keywords are certain words in your article that describe certain aspects. So for example, you always have, so the reader of the article should know what keywords or the terms are you are using. For astronomy, for example, when we speak about the keyword for us would be electron, neutron, proton, um, light year, parsec. So if a reader doesn't know what those keywords are that describes it, so you don't want to describe, for example, in your article what a light year is. The reader should automatically know it. But if a reader doesn't know what a light year is, a keyword would be light year, meaning the reader can read up on light years first before reading the article. So may we include pictures in articles? Yes, you're more allowed to include pictures. What does the abstract comprise again? So the abstract is a summary of the entire article. So your abstract must contain your introduction, your results, and your conclusion. So is that a specific layout? So yes, that is a specific layout. So you will see if you, in your scientific careers, you will write a lot of articles. This is the general article format we use to write. So here and there, depending on which journal you are publishing your article in, there might be a little bit of a difference, but this is the generic article writing style. So I know this will be your first time writing articles. Um, so this is just to give you an introduction to writing articles. And yes, you answer your questions in the article as well. So let me see, questions. So max 3 pages. So yes, I would preferably have max 3 pages. If you go half a page or page over the limit, that's not the end of the world. But I would like you guys to stick to 3 pages. The reason I'm saying this, sometimes when you publish an article in a journal, you have space restrictions. So the idea is to get your points and your research through in the least amount of writing. Font type, so usually it will be an IEEE reference guide, but font type is preferably Arial or Times New Roman. Font size will be in the guide itself, but usually it would be, headings will be size 12 and your paragraphs will be size 11. So the marking guide, I'm not going to provide you guys with the marking guide, but I will quickly show you the marking guide. So this, in this lecture, will be the only time that you guys will see the marking guide and see how it looks like. I'm just going to share it. Yes, you have a question. So just to make the marking easier, your assignment is going to be worth 100 marks. So yeah, I have descriptions. So for very weak is between 0 and 3.4. Need to work is between 3.5 and 4.9. Satisfactory will be between 5 and 6.4. Good between 6.5 and 7.4. And excellent between 7.5 and 10. So question, make a scale drawing on your sheet of paper of the landmarks on your horizon as seen from your point of observations. What does this mean? So that means where you are standing and making your observations from, you just need a reference frame. So if there's a tree somewhere in the background, include a tree. If is there a building in the background, include a building. This is to make sure that you are making the observations from the same point every day, and also that will help you to determining the diameter of the moon. So does the abstract reveal the results, or should we limit the information? Yes, the abstract reveals the results, but you don't limit the information. So your questions that you're going to answer is going to count 10 marks. Your observations, so your sketch that you are providing me with, is going to be 10 marks. One thing you can do is, I want your sketch inside your article. You can put it as a small sketch in one of the columns, but please attach your full drawing as well as an attachment. And that won't count as pages for the article. Then the next thing you want to look at as logic and background information. Then calculation of the diameter of the moon. The research you have done into what the moon is doing, because the moon will be doing something during those 10 days. I'm not going to tell you what. I'm going to wait for one of you guys to bring it up in the next couple of weeks. Then I'm going to look at your conclusion. Then I'm going to look at your referencing. Did you do referencing correctly, and do you have references? Then I'm going to look at formatting and layout. So spelling and grammar, and your use of language and scientific writing. One thing to always keep in mind when you're writing these documents and doing scientific writing, and a few people made this mistake last year, always remember this for your lab and prac reports as well. You always write in the third person. So for example, you don't write, I have done these observations over the past 10 days. Or we have done these observations, we have done this experiment. You never write in first person. You write, the moon was observed in the last 10 days. An experiment was conducted. Never in first person, always in third person. And then lastly, I will look at your scientific content. So I am here to help you guys with this. So if you have questions during your observations, if you have questions during your writing of the article, if you need help with something, if you need my input, I am more than welcome, I'm more than willing to help you guys with this. So what is meant with scientific content? So scientific content is, you speak about actually the science behind everything. Because last year, some students in their article has written more about the beauty of the moon and has written more about the background of which astronomers study the moon than actually answering the questions I asked. So that is why I asked for scientific content. Awesome. So any more questions on the assignment? If not, then let's continue with tonight's lecture. So last week we ended up the in our discussion with refracting and reflecting telescopes. And also we started looking at difference of a big optical telescope and a big radio telescope. Do you guys have any questions? Yes, Mr. Levuyo.
Good evening, sir.
Hi.
So before we proceed to the new works, I just wanted to ask a few questions about the old work, if that's okay.
Yes. Yes. Go ahead.
So I wanted to ask if parallax only observed because because of the stars in the background, or can you observe it even though there was no stars?
You can observe it even though there are no stars. So let me get a whiteboard out. This will be easier to explain it this way. So the one way we do parallax is, remember, when you stretch your arm out and you cover an object in a distance with your thumb, and you close your right eye, look with your left eye, and see where the object in your thumb is. Then close your left eye and look for your right eye. You will see there's a slight difference in the two images you are seeing with your eyes. That's because your eyes are about, what, 7 centimeters apart, so there's an angle between your eyes. So if I draw this, this is our one eye. Now for some weird reason I can't see my cursor. Here it is, that's the one eye. This is badly drawn one eye. Here's the object we are looking at. So we are looking at this way, the incoming light rays. Here is the other light rays. We know what this distance is. So the angle that this makes is the parallax angle. So in terms of astronomy, how we do it is we have the sun, we have the Earth orbiting the sun, so this is a year apart, so this is just a normal orbit around the sun. We know this distance is 1 AU. We know this distance is 1 AU. So when we are looking at an object that is far away, we take an observation from this side, and we take an observation from this side, and then we look at this angle measured to find the parallax. The only problem with this is the further an object is away, the smaller our parallax angle is. So for objects that are super far away, we can't use parallax because we can't see a shift between the two. And to solve this problem, we're going to discuss in next week's lectures. Does that answer your question, Mr. Levuyo?
So I understand. Okay, I don't necessarily understand. So how does it look? Because okay, I don't understand how you would actually see it. I understand there's a parallax, but I don't see it.
So in the upcoming lecture, we will have an example actually to see how you determine parallax and how it's used in our everyday lives. So I think if you just wait another week, then this will answer your question a little bit better.
Okay, yes, sir.
And you said you have other questions as well.
Yes, sir. So I want to say, sir, I think it's more of an observation that I just wanted to ask. So here in South Africa, so when it's winter, we usually see a lot more stars than we do in the summer. Is it because can you please explain that to me?
Okay, I'll explain that. So that's also a point from perspective of where you are in the country. But also remember, everything in the universe is moving. The Earth is rotating around its own axis. The Earth is rotating around the Sun. The Sun is rotating around the galaxies. So everything is moving. So usually in the way we are in our orbit around the Sun, so let me draw this. We have the Sun, we have our orbit around the Sun, and let's draw Earth over here, over here, over here, over here. So remember, Earth is canted at an angle of approximately 23 degrees. So taking this angle in consideration, when Earth is on this side, more sun rays will hit the southern hemisphere than the northern hemisphere. So that's why we have summer here, winter here. But going 6 months further, we have the Earth over here. Remember, it's canted. So meaning northern hemisphere will receive more sunlight than the southern hemisphere. So that means here will be summer and over here will be winter. But going around the sun, we know that over here we basically have a view from Earth in this quadrant here. From here, meaning we have a view in this quadrant here. From this here, we have a view from this quadrant here, and when Earth is here, we have a view of this quadrant here. So what we see in a night sky depends on where we are in our orbit around the sun. And when we look at constellations, because we are moving around the sun, usually half of the constellations will be visible during summer months, and half of the constellations will be visible during winter months. And that is due to the fact that we are moving around the sun. And then why it also might seem that stars are more clear during the winter months is the atmosphere is much more stable. So during summer months when it's hot, we have rising heat going up in the atmosphere, and that causes waves and high currents in the atmosphere. That is not favorable. So in the cooler winter months, there's not much rising air, so the atmosphere is a lot cooler, and then we can see more stars as well. So usually when you look through a telescope at the night sky, you want it basically to be as cold as possible and as dry as possible for the atmosphere to be as stable as possible. So Usually the best time to observe stars will be the day after cold front has hit a certain area, because then the atmosphere will be at its stablest. Does that answer your question?
So it has nothing to do with us, like, so for example, so isn't it you say like in different in different times of the year we see different parts of the sky. So it's not because like in some parts of the in some parts of the year we face more towards like the center of the galaxy, and that's where most stars would be.
Yes, that does, but it all depends on where we are in our orbit around the sun.
Okay, thank you, sir.
Pleasure. Do you have any more questions?
Yes, sir. Do the planets move in the same like direction as the Earth's rotation?
Ah, that's also a fun question. So basically, most of the planets rotate the same way as Earth, and most planets also rotate in the same planetary disk. But it is also something we are going to discuss quite deeply in the next few lectures.
Okay, so I think that's all I have, sir.
Okay, cool. So let me share the slides again for this evening. Let me just find the correct slide. So last week we ended off here. So now when you continue the discussion with two ways to do it, refracting or reflecting telescopes that we talked about. Astronomers use the term seeing to refer to the amount of image blurring due to atmospheric conditions. A related phenomenon is the twinkling of stars. Stars twinkle as caused by turbulence in Earth's atmosphere, and a star near the horizon, where you look through more air, will twinkle and blur more than a star overhead. So in this image, so in image A, stars are so far away that the images looks like points. But the wave-like characteristic of light causes each star image to be surrounded with diffraction fringes, much magnified in these computer models. So in B, two stars close to each other have overlapping diffraction fringes and become impossible to detect separately. So two ways to do it. So reflecting and reflecting. So one thing that's important with telescopes is the opening that we have. So what would you guys think? What would be better? A telescope with a large opening or a telescope with a small opening? Yes. So the larger the opening, the more light we can capture from the object we are looking at. So here in image A on the left half of this photograph is a galaxy and is from an image recorded on a night of poor seeing visibility. So small details are blurred. So on the right hand side image is the same photo, and it is form of an image recorded at night when Earth's atmosphere above the telescope was steady and seeing was better. So much more detail is visible under good seeing conditions. So from this it is clear the more stable the atmosphere, the better it is for our observing. So another thing to remember is reasoning with numbers. This is in the textbook, and this is also something to remember for the test and exam. So the light gathering power of a telescope is proportional to the area of the primary mirror or lens. A primary with a large area gathers a large amount of light. The area of the circular lens of a mirror diameter d is given by this equation. That's just pure math. To compare the relative light gathering powers, so we call it LGPs, light gathering powers, of two telescopes A and B, you can calculate the ratio of the areas of their primaries, which is the ratio of the diameter squared. So light gathering power of A over light gathering power of B is the diameter of A over the diameter of B squared. So example A, suppose you compare a 4 centimeter telescope with a 24 centimeter telescope. How much more light will the larger telescope gather? So the light gathering power of the 24 telescope divide the light gathering power of the 4 centimeter telescope equals 24 divided by 4 to the power 2. So it's 6 to the power 2, so 36 times more light can be detected. So that's why it's more important, you can see it mathematically, why a bigger telescope is more important. So, example B, your dark adapted eyes acts like a telescope with a diameter of about 0.8 centimeter. The maximum diameter of the pupil. So how much more light can you gather if you use a 24 centimeter telescope relative to your unaided eye? So if you plug it in your formula, you can gather 900 more times with a 24 meter telescope than with your naked eye. And then the resolving power of a telescope is the angular distance between two stars that are just barely visible through the telescope as separate images. So yes, the bigger number is always on top. So the resolving power alpha in arc seconds of a telescope with diameter d in meters, that collecting light of wavelength nanometers equals, so remember this is just another given formula, so alpha, that is in arc seconds, equals 2.06 times 10 to the power 5 wavelength divided by diameter. So this is just a formula you can use. So the multiplication factor of 2.06 times 10 to the power 5 is the conversion between radians and arc seconds that you first learned in the small angular formula, remember we did a couple of weeks back. If the wavelength of light being studied is assumed to be 550 nanometers in the middle of the visual band, then the above formula simplifies to the following. It's just plug and play. So example C, what is the resolving power of a 10 centimeter telescope? So we have here our formula, resolving power equals 2.06 times 10 to the power 5, 550 nanometers over 10 centimeters, and that's 1.13 arc seconds. So in other words, using a 10 centimeter or 4-inch diameter telescope, you should be able to distinguish the separate points of light in a pair of stars further apart than 1.1 arc seconds. If the lenses are of good quality, if the seeing is good, stars close together then will be blurred together into a single image by diffraction fringes. So question D. The same resolving power formula can be applied to a radio telescope. What is the observed resolving power of a radio telescope of 100 meters? So we plug that into our formula, and voila, same thing, straightforward. So note how poor the resolution even of a large radio dish is compared with optical telescopes. The resolution limit of 435 arc seconds corresponds to almost a quarter of the diameter of the full moon. So the magnifying power M of a telescope is the ratio of the focal length of the primary lens or mirror divided by the focal length of the eyepiece. So straightforward, plug and play. So what is the magnification of a telescope with a primary mirror focal length of 80 centimeters if it's used with an eyepiece with a focal length of 0.5 centimeters? Solution: the magnification is 80 divided by 0.5, so it is 160 power. You guys all happy with this? Straightforward plug and play? Awesome. So let's speak a little bit about different observatories. So astronomers avoid cities because light pollution, the brightening of the night sky by light scattered from artificial outdoor lighting, can make it impossible to see faint objects. Radio astronomers face a problem of radio interference comparable to visible light pollution. Weak radio waves from the cosmos are easily drowned by human-made radio noise. Everything from automobiles with faulty spark plugs to poorly designed communication systems. A few narrow radio bands are reserved for astronomy research, but even those are often contaminated by stray signals. To avoid that noise and have the radio equipment of a dark sky, astronomers locate radio telescopes as far from civilization as possible, hidden in mountain valleys or in remote deserts. They are able to study the universe protected from humanity's radio output. So if you remember from slides from an introductory lesson, that's why Hatra, where I am, is in a valley and we have a radio exclusion zone. That's why where the Green Bank radio telescope has an radio exclusion zone of 90 miles. And you all understand why light pollution is an important factor for optical telescopes and why Sutherland is built far away from civilization. And something interesting, I've spent some time in Sutherland. When sun sets, you have shutters in front of your windows to make sure that you don't interfere and cause light pollution on the telescope. For most of the 20th century, astronomers faced a serious limitation of the size of astronomical telescopes. Telescopes' mirrors were made thick to avoid bending that would distort the reflecting surface, but those thick mirrors were heavy. The 5-meter mirror on Mount Polymer weighs 14.5 tons. Those old-fashioned telescopes were not only big and heavy, but also very expensive. Today's astronomers have solved these problems in a number of ways, and can you guys guess how we solve those problems? Multi-sectioned mirrors is one option, arrays of telescopes is another option. But before we're looking at arrays of telescopes, let's look at normal optical telescope. How do we solve these problems? Use of lighter composite materials, yes. So, here are a few of the methods we use. So firstly, we use not conventional design reflecting telescopes. So conventional design reflecting telescopes use large solid heavy mirrors to focus starlight to a prime focus, or by using a secondary mirror to a Cassegrain focus. So other telescopes has a Newtonian focus or a Schmidt-Cassegrain focus. Secondly, telescopes must have a sidereal drive to follow the stars. An equatorial mount with motion around the polar axis is the conventional way to provide that motion. Today, astronomers can build simpler, lightweight telescopes on old azimuth mounts that depend on computers to move the telescope so that it follows the apparent motion of the stars as Earth rotates without having equatorial mount and polar axis. So what's meant with that is, let me get a whiteboard out. When you have a telescope with, and so let's draw this. This is not going to be one of the best drawings, but it will get a point across. We will have a telescope. It will have 3 legs. So this will be north, east, and south directly. Then there would be an equatorial gear that moves directly from south to east. Sorry, not east, this is west. Where am I mind tonight? And then there will be another gear running this way, and that will go from north to south. And that usually is a lot of weight, a lot of construction. But what we do now these days is we have our telescope. So we have a strong frame. And then we call this an alt-azimuth mount. So it will have a ball joint on the top. And then our telescope will fit over this ball joint. So you can think about this ball joint as your knee or arm socket. And the telescope will from there be stuck on this, and computers will slip this around anywhere possible on our ball joint. So we have computers with different motors that can do it, so it just becomes easier using an alt-azimuth system. Yes, Mr. Levuyo.
So, are radio telescopes made out of like a specific material that allow these higher frequency what are they? These high frequency light to be able to interact with the material?
So when we choose the construction material of our telescopes, that is an important factor because it all comes down to what do we want to study. For example, if we want to look at X-rays, X-ray telescopes, and we just have a giant mirror, X-rays will move through the mirror. So then we will need a lens or a mirror constructed of a material that will reflect X-rays, and X-rays won't penetrate it. If we go to visible light, then we need a mirror, as we know, a mirror or a lens. If we go to radio waves, depending on the frequency we are looking at, that we can use either a solid surface or a grid-like surface. It all depends on what we want to observe.
Thank you, sir.
Pleasure. And then we have active optics. So computer control of the shape of a telescope's main mirror allows the use of thin, lightweight mirrors. So they call it floppy mirror, so that means we add a few smaller mirrors to create a big mirror. So that's reduce the weight of the mirrors and reduces the weight of the telescope, and making it stronger and less expensive. Also, thin mirrors cool and reach a stable shape faster at nightfall, producing better images during most of the night. So we, instead of having one giant mirror, we have smaller mirrors stuck together, each with actuators and motor control, and active optics will focus each of those mirrors to get the sharpest image as possible. So here in this image is how a normal telescope will operate. So here we can see remained with a Cassegrain focus is we have our incoming light rays coming in. This is our primary mirror. The light rays is reflected to a secondary mirror. And from the secondary mirror, it's reflected to our eyepiece that's over here, and that's a Cassegrain focus. So a Newtonian mirror is we will have our incoming lights hit the mirror, bounce up to the secondary mirror and out to eyepiece on the side. And then we try to combine these two by having your incoming light rays coming in. It reflects to the secondary mirror out the eyepiece that is bended, and that's a Schmidt-Cassegrain telescope. So here in this image we can see the prime focus cage, secondary mirror, primary mirror. Here we can see a small astronomer standing to show the size of the telescope. And here is our Cassegrain focus, where will be our recording equipment. So here is what I described with the different mounts. So here we have our equatorial mount. Then over here we have our old azimuth mount. So here we can see the big mirror together, floppy mirror or a segmented mirror. You guys still happy and still following? Awesome. So here we can see modern engineering techniques and high-speed computers have allowed astronomers to build and use new giant telescopes with unique designs. So here we can see the optical infrared and microwave radio telescopes at 4,200 meters above sea level at Miyano Key in Hawaii. So the high altitude, low atmospheric moisture, lack of nearby large cities, and location near the equator make this mountain one of the best places on Earth to build an observatory. Yes, Hubble is an optical telescope. So remember, when we build telescopes, we want them as dry, places as dry as possible, places as cold as possible, to get the atmosphere stable enough. So usually, and also places where there's no water vapor. So to solve most of these problems, it's usually at a high altitude. So here is a few of these optical telescopes. So here we have the large binocular telescope that uses two same way your eyes work. We have the very large telescope, and here we have only 12 of the 36 primary mirror segments had been installed at the time of this photo of the VLT. And then we have the giant Millikan telescope, the 30-meter telescopes that proposed. And then currently this is going to start construction phase, is the European Extremely Large Telescope, which this will be a 39-meter diameter mirror. This will be the world's largest optical telescope that's currently being built. Oh yes, you're correct. They did start in 2017. And then the biggest telescope, optical telescope we have in the southern hemisphere is the SALT telescope, South African Large Telescope. It also has constructed out of a lot of different mirrors, and it's roughly 11 meters in diameter. So yes, then let's go back a few slides. So yes, they are exposed to the weather. So what we do with these telescopes, we build these domes around telescopes. So we can't just open up the telescope at any time because the heat fluctuations of the difference between the air temperature inside the telescope and the temperature outside the telescope, so meaning the dome, differs because of heat working on different materials, stretching it and crimping it. We can actually crack a mirror. So what we do is we keep the air temperature inside these domes as the same temperature as outside of these domes. And as soon as we start observations, we open these doors, exposing the telescope and its lenses and mirrors. And then it will be at the correct temperature and we won't have these issues. And then once we've done observing, we close these doors and the telescopes are protected again. And then we have modern radio telescopes. So the dish reflector of a radio telescope, like the mirror of a reflecting telescope, collects the focus's radiation. Although a radio telescope's dish may be tens or hundreds of meters in diameter, the receiver antenna may be small as your hand. So this is the Arecibo radio telescope. It was the world's second largest telescope. And unfortunately, it collapsed in December of last year. So this is built in Puerto Rico, 305 meters across. So we have our incoming radio electromagnetic waves that's reflected up to our receiver assembly up here. So you guys are still comfortable with the difference between optical and radio telescopes and why we build telescopes a certain size to pick up certain wavelengths of what we are observing. So these mirrors aren't just ordinary mirrors, they are constructed out of material depending on what we want to observe. If we use a normal mirror and want to detect X-rays, they just pass through a mirror and that's useless. So we need a surface that can reflect X-rays. So it all depends on what the telescope is designed to do. So a radio astronomer works under two disadvantages relative to optical astronomers, so poor resolution and low signal intensity. Recall that the resolving power of a telescope depends on the diameter of the primary lens or mirror and also on the wavelengths of the radiation. At very long wavelengths, like those of radio waves, the diffraction fringes are relatively large. This means that images or maps from individual radio telescopes generally don't show such fine details as seen in optical images. The second handicap radio astronomers face is the low intensity of radio signals. You learned earlier that the energy of a photon depends on its wavelengths. Photons of radio energy have such long wavelengths that the individual energies are quite low. The cosmic radio signals arriving at Earth are astonishingly weak, a million to a billion times weaker than a signal from a commercial radio station. To get detectable signals focused on antenna, radio astronomers must build large collecting areas, either as single or large dishes, or by combining arrays of smaller dishes. Even then, because the radio energy from celestial objects is so weak, it must be strongly amplified before it can be measured and recorded. Ground-based telescopes, the telescope performance is limited by Earth's atmosphere, turbulence, and transparency. As you will learn, there are sophisticated techniques that partly compensate for atmospheric seeing, but a telescope in space has no such problem, and its resolution is defined only by diffraction. Also, a telescope on the ground must look through one of two open atmospheric windows in the visible or radio parts of the electromagnetic spectrum. Most types of electromagnetic radiation arriving here from the universe are infrared, ultraviolet, X-rays, and gamma rays. And they do not reach Earth's surface because they are partly or completely absorbed by Earth's atmosphere. To operate at those blacked wavelengths, telescopes must go to high altitudes or into space. As you will learn in the next few chapters, objects that are cooler than stars, such as stars that are forming, emit mostly infrared and radio radiation and relatively little visible light. In contrast, cosmic catastrophes, such as exploding stars, make mostly gamma rays and X-rays. Combining information from as wide a variety of wavelengths as possible allows astronomers to gain a more complete understanding of the universe. So taking this into consideration, we only have 8 telescopes currently that can detect X-rays, and one of them is in orbit, the X-ray Chandra telescope that's in space. So my question, can the satellites in space out of the atmosphere disturb the telescopes on the ground, such as radio telescopes? Yes, that happens. So one of the biggest problems now for astronomy is Elon Musk's SpaceX Starlink satellites. That disturbs optical telescopes and radio telescopes. In optical telescopes is, if they are moving around Earth, their solar panels are reflecting sunlight. So if you are observing a certain object through an optical telescope and you have these string of Starlink satellites moving across your image, flashing back sunlight, then your image or your observation is ruined. In radio telescopes, those satellites are operating on a communication frequency of 5.5 gigahertz, and we are observing certain objects between 5 and 6 gigahertz. So again, that blinds the radio telescopes as well. So currently the astronomy community is trying to work with Elon Musk to see if we can find a solution to solve this problem. So a few of our airborne and space observatories. It's a pleasure. So the most popular one is probably the Hubble Space Telescope. Why don't we get more telescopes in space? Purely the cost. It's expensive to put a telescope in orbit. And then secondly, it becomes very expensive to do maintenance on those telescopes. So the Hubble Space Telescope, named after Edwin Hubble, the astronomer who discovered the expansion of the universe. So we will learn about Hubble's constant. So the Hubble Space Telescope is the most successful observatory in history. It was launched in 1990 and contains a 2.4 meter mirror, plus instruments with which it can observe visible, near ultraviolet and near infrared light. It is controlled from a research center on Earth and observed almost continuously. Unless the telescope has time to complete only a fraction of the projects proposed by astronomers from around the world. Most of the observations Hubble makes are at visual wavelengths, so its greatest advantage is being located above Earth's atmosphere in the lack of seeing distortion. It therefore can detect fine detail, and because it concentrates lights into sharp images, it can detect extremely faint objects. The Hubble telescope is as big as a city bus. It has been visited a number of times by the space shuttle, so that astronomers could service its components and install new cameras and other instruments. Thanks to the work of the Space Shuttle astronaut crew that visited in 2009 and refurbished the telescope's instruments, batteries, and gyroscopes, Hubble will almost certainly last until its replacement by the James Webb Telescope. The James Webb Telescope will carry a cluster of beryllium segments that will open in space to form a 6.5 meter telescope. So Currently, the James Webb Telescope is over budget, and over time, it was supposed to be finished and launched in 2017, but it was now pushed back now to later this year. So hopefully, it will get launched this year. So here is an image of the Hubble Space Telescope. Here is the James Webb Telescope, how it will look like when it's completed. And then the Herschel Space Observatory. So the Herschel Space Observatory is the Herschel Infrared Space Telescope that carried a 3-meter mirror and instruments cooled almost to absolute zero and was constructed primarily to look at infrared. So, a question I would like to ask you guys. How do we currently observe infrared? So how do we conduct infrared astronomy? Because we have a problem with the atmosphere. Because infrared is blocked by water vapor. So any suggestions? Yes, so one option is to put it in space, but there's a second option as well. Not a drier climate. Yes, airborne. So in addition to the atmospheric windows at visual and radio wavelengths, you have already learned about, there are also a few narrow windows at short infrared wavelengths accessible from the ground, especially from high mountains such as Mauna Kea. So, however, most infrared wavelengths are blocked, especially by water vapor absorption. Also, Earth's atmosphere itself glows in the far infrared. So observations at very long infrared wavelengths can be made only from telescopes carried to high altitudes by aircraft or balloons or launched entirely out of the atmosphere aboard spacecraft. So yes, you are correct, Mr. Groenewald. SOFIA. SOFIA stands for the Stratospheric Observatory for Infrared Astronomy, so it's a joint project of NASA and the German Aerospace Center DLR, and it flies to an altitude of 14 kilometers, so 45,000 feet. We can collect infrared radiation at far infrared wavelengths that are unabsorbable even from high mountaintops. And then B, we can see infrared images of the planet Jupiter at wavelengths of 5.4, 24, and 37 microns, made during SOFIA's first flight in May 2010, compared with the visual wavelength image on the left-hand side. The white stripe in the infrared image is a region of relatively transparent clouds through which the warm interior of the planet can be seen. So here we can see SOFIA with the telescope, visual image of Jupiter, infrared image of Jupiter. And then, how do we do high energy astronomy? Unlike infrared emitting objects, gamma ray, X-ray, and ultraviolet sources in the universe are difficult to observe because the telescopes must be located high in Earth's atmosphere or in space. Some high-energy astronomy satellites have been general-purpose telescopes that can observe many different kinds of objects. The largest X-ray telescope to date is the Chandra X-ray Observatory. Chandra operates in orbit that extends a third to the way to the moon. Focusing X-rays is difficult because they penetrate into mirrors. So astronomers devise cylindrical mirrors in which the X-rays reflect at shallow angles from the polished inside of the cylinders to form images on the X-ray detectors. Chandra Observatory has made important discoveries about everything from star formation to monster black holes in distant galaxies, that will be described in later chapters. So here we can see how it forms. So X-rays that hit a mirror at grazing angles are reflected like a pebble skipping on a pond. This X-ray telescope mirrors, like the ones in Chandra, are shaped like barrels rather than dishes. So what that means is, with this is, if we have our incoming X-rays, in our detector, it just moves straight through it or gets reflected off to it. So then we have these cylindrical mirrors that will focus the X-rays precisely on our detector, and then we can monitor X-rays. One of the first gamma ray observatories was the Compton Gamma Ray Observatory, launched in 1991. It mapped the entire sky at gamma ray wavelengths. The European Integrals International Gamma Ray Astrophysics Laboratory satellite was launched in 2002 and has been very productive in a study of violent eruptions of stars and black holes. The Fermi Gamma Ray Space Telescope, launched in 2008, is capable of mapping large areas of the sky to high sensitivity. So, also high energy astronomy. So here we can see astronomical cameras with array detectors must be cooled to low temperatures to operate properly. And that is especially true for infrared cameras. We do this on optical telescopes, we do this on radio telescopes, we do this on infrared telescopes. We cool in radio telescopes, it's our receivers. Here in this case, it is the infrared cameras. We cool it down to as close as absolute zero as possible to stop noise from the electronics on our telescopes, because electron movement causes noise that we can detect, and that will cause havoc on our images. So for example, at HeartRAO, we keep our receivers at 12 Kelvin, that is approximately minus 260 degrees Celsius. Any questions so far?
So I have a question. So,
Yes, Mr.
so for labs at like LIGO, so the with the experiments they're running for searching for gravitational waves. So will that be used with astronomy to sort of find these phenomena, like yes, those type of things.
Yes. So
And so
before we had LIGO, we used our different telescopes to try to detect for gravitational waves, but now LIGO is a purposefully built instrument specifically built to detecting gravitational waves. But we used in conjunction with telescopes as well.
So what type of information do you get from gravitational from the LIGO experiment? If I'm right, so I'm like, I assume that this experiment can also be considered some type of telescope.
Yes, and we are leading up to it in this lecture. So in a couple of slides, we'll have a nice discussion on LIGO.
Thank you,
So
sir.
I want to open up a discussion for the class. So how do you guys think we are doing high energy astronomy? So we now know how to look at X-rays, infrared, but how do we look at particles with even more power, if I could put it that way? So yes, that's why we have facilities such as CERN, but what kind of detectors can we also use to study these besides CERN? How do we detect these high energy particles from space?
So do you know about that experiment to find I think it was the muon where they put like like I think it was like 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 it was under the earth, and then like every time a particle hit that sort of I think it was a room. I don't know what it was. It would light up.
Yes, that is exactly what happened. So I'm not exactly too familiar with the technical details of the muon experiment, but that was built inside a mountain. Then at a certain liquid, if a particle interact with it, it will start to glow. And then they will have detectors on top of the mountain, detectors inside the mountain, and that's how they detect these particles. And that's the same thing we do in astronomy as well. So just looking through a telescope doesn't tell you much. A star looks like a point of light. A planet looks like a little disk. A galaxy looks like a hazy patch. To use a research telescope to learn about the universe, you need to carefully analyze the light the telescope gathers. Special instruments attached to the telescopes make that possible. So we have imaging systems and photometers. Just like the photographic plate was the first device used by astronomers to record images of celestial objects, so photographic plates can detect faint objects in long time exposures and can be stored for later analysis. Brightness of objects imaged on a photographic plate can be measured, but only with a lot of hard work that yields just moderate precision. Astronomers also build photometers, sensitive light meters used to measure the brightness of individual objects very precisely. Present-day astronomers use charged-coupled devices, so CCDs, that's what's in our cameras today, as both image recording devices and photometers. A CCD is a specialized computer chip containing millions of microscopic light detectors arranged in an array about the size of a postage stamp. CCD chips have replaced photographic plates because they have some dramatic advantages. CCDs are much more sensitive than photographic plates and can detect both bright and faint objects in a single exposure. Also, CCD images are digitized, meaning converted to numerical data, and this can be stored in a computer's memory for later analysis. Although astronomy research CCDs are extremely sensitive and therefore expensive, less sophisticated CCDs are now part of everyday life. So, question, how do they tell that those little patches are actually galaxies? Could it be anything? How to tell it all? So, we can clearly see it's a galaxy. So, from a telescope, we can see it almost looks like a cloud in space, if I can put it that way. And then from there on, we can look at the different emissions and determine it's a galaxy. So is there a difference between high energy astronomy and X-ray astronomy? No, it's not a difference. X-ray astronomy is a sub-part of high energy astronomy. Infrared astronomers use array detectors that are similar in operation to optical CCDs. At other wavelengths, photometers are still used for measuring brightness of celestial objects. Astronomical images are often reproduced as negatives, with the sky white and the stars dark. That makes the faint parts of the image easier to see. Astronomers also manipulate images to produce representable color images, also known as false color images, in which the colors represent different aspects of the object, such as intensity rather than visual color. So here we can see images of galaxy NGC 891 in true color. It's etched on and contains a thick dust clouds. So in image A, we can see astronomical images can be manipulated to bring out difficult to see details. The color photo of this galaxy is dark, and the dust clouds in the galaxy's central plane do not show very well. So in B, we rather look at the negative image was produced to show the dust clouds more clearly. So you guys are familiar with the difference between the normal visual and the negative image? So with any photo editing app, you can usually pick the negative of an image, and that's just the image flipped to basically the negative side, if you want to put it mathematically. That's the same way we would develop old films back in day. By doing this way, so where there's a bright intensity, that will rather be dark, and where there's less intensity, that will rather be light. So normal true color, the more the lighter the object, the higher the intensity, the darker the object, the less the intensity. So if you flip it around, you can see a little bit more detail. So, astronomical instruments and techniques. What else can we learn? So in this image, we can see a typical weather map uses contours with added color to show which areas are likely to receive precipitation, so meaning rain, and of what type. A radio image of Tycho supernova remnant, the expanding shell of a gas produced by the explosion of the star first seen on Earth in 1572. This image representational color code shows intensity of radiation at just one wavelength. In image C, we can see a picture of galaxy M101, composed of a visual wavelength image from the Hubble Space Telescope, combined with an X-ray image made by the Chandra X-ray Observatory, plus an infrared image from the Spitzer Space Telescope. In this representational color image, the blue shows X-rays from hot gas heated by exploding stars and black holes, where red shows infrared emissions from cool, dusty clouds of gas in which stars are being born. Then, spectrographs. This is where my research field is and what I'm doing. Is to analyze light in detail. Astronomers spread out the light according to wavelength, color, in a function performed by a spectrograph. You can understand how this works if you imagine repeating an experiment performed by Isaac Newton in 1666. Newton bored a small hole in a window shutter of his room to admit a thin beam of sunlight. When he placed a prism in the beam, it spread the light into a beautiful spectrum that was splashed across his wall. From that and related experiments, Newton concluded that white light is made of a mixture of all the colors. Almost all modern spectrographs use a grating rather than a prism. Grating is a piece of glass or metal with thousands of microscopic parallel grooves scribed into its surface. Different wavelengths of light reflect from the grating at slightly different angles, so the white light is spread into a vacuum. You have probably noticed this effect when you look at the closely spaced lines etched into a music CD or video DVD as the tip of the disc. Different colors flash across the surface. So here we can see how a spectral works. So the spectrum of an astronomical object can contain hundreds of spectral lines. So dark or blurred lines that cross the spectrum at specific wavelengths. So here we can spread it, and this principle works with radio waves as well. In radio astronomy, we don't call it the spectrograph, but the spectrometer. So here is the telescope I work on primarily. It's the Archimedes big 26-meter telescope at Hartrau. And I'm working on the spectrometer and spectroscopy done by this telescope. Then I also went to the world's third largest telescope. I've spoken about this before, the Green Bank telescope, where I also did spectroscopy. So how does a spectrometer look like? So this is the bare bones of a spectrometer. This is called an FPGA, Field Programmable Gate Array. That's a processor that falls between a CPU and a GPU. So you have your incoming information coming through your telescope, and all the processing and the spectrum part of it, so the spectral lines we're looking at, is processed on this FPGA. So question, how many people do you collaborate with on your research? So yeah, there's a lot of people. So the primary group I'm collaborating with is called CASPER, the Collaboration for Astronomy Signal Processing and Electronics Research. The CASPER group is situated in the University of California, Berkeley, but a lot of people, a lot of institutes is part of the CASPER group. And CASPER primarily develops these detectors for a lot of telescopes around the world. So the entire MeerKAT makes use of the research done by CASPER, and HADRA makes use of the work done by CASPER, GreenBank makes use of CASPER. So we are actually a big collaboration. Yes, my job is very fulfilling. I love every moment of what I do. So, from this spectrometer, this is a typical image we would see if we look at the PIA data itself. So we can construct the image from this, but this is the PIA data itself. So this is a methanol maser we observed at roughly 6.6 gigahertz. So in our introductory lesson, I described what the maser is, but just to recap, maser stands for microwave amplification by stimulation of emitted radiation. A laser stands for light amplification by stimulation of emitted radiation. So laser and a maser is the same thing, only a laser emits light and a maser emits microwaves. So usually around stars are these molecular clouds. So this is a molecular cloud consisting of methanol. So if there's a charged particle that moves through this molecular cloud, the electrons will jump into a higher valence orbit, radiating more energy, and we can pick that up through our telescopes. So this right here we see is 6.6 gigahertz corresponds to methanol, because remember, every element, every composition of material, gas, everything has either an emission spectrum or a absorption spectrum, meaning either it will emit radiation at a certain frequency. So remember, light waves is just radiation at visible frequencies, or an object will absorb certain frequencies. So right here, we can see methanol spike at 6.6 gigahertz. So meaning, if one of these masers flares up and becomes more intense, meaning there is charged particles moving through that molecular cloud, meaning there's something happening in the vicinity of that molecular cloud that we can investigate. So I've spoken about adaptive optics to counter the effect of the instability and turbulence in our atmosphere. So you have already learned about active optics, a technique to adjust the shape of the telescope optic slowly, compensating for effects of changing temperature as well as gravity bending the mirror when the telescope points at different locations in the sky. Adaptive optics is a more sophisticated technique that uses high-speed computers to monitor the distortion produced by the turbulence in Earth's atmosphere and rapidly alter some optical components to correct the telescope image, so sharpening the fuzzy blob into a crisp picture. So here on the image on the left, we can see an A where adaptive optics is off, and then in the image next right to it is where adaptive optics is on. And then in image B, we can see the laser beam shown leaving one of the Keck telescopes produced an artificial star in a field of view. An adaptive optics system uses the laser guide star as a reference to reduce seeing distortions and entire image. This is just one way to calibrate the telescope. Then we get to an object called interferometry. So in optical telescopes, we call it interferometry. In radio telescopes, we call it correlation. I prefer to use the term correlation. So one of the reasons astronomers build big telescopes is to increase resolving power. And astronomers have been able to achieve very high resolution by connecting multiple telescopes together to work. In a sense, if they comprised a single very large telescope, this method, emphasizing a virtual large telescope from two or more smaller telescopes, is known as interferometry. So looking from this in an optical perspective, instead of building one giant telescope, we build a few smaller telescopes, and these beams combine to produce the final image. So an astronomical interferometer, smaller telescopes can combine their light to simulate a larger telescope with a resolution set by the separation of the smaller telescopes. So by making use of three smaller telescopes, we can virtually construct a one giant telescope. We do the exact same thing with radio telescopes. So the image on the left, you will probably remember from sci-fi movies, is the very large array from very large array in the United States. And the image on the right is Meerkat, that is currently 64 antennas. So this is just a representation, and this will become roughly 3,500 these antennas. They will construct a telescope that's basically 1 square kilometer in diameter. And then we get to an interesting part called non-electromagnetic astronomy. So other types of energy also arrive here, bearing information from the rest of the universe, and deserve a brief mention. So remember, everything we observe apart from electromagnetic spectrum, but how do we observe something that's not part of the electromagnetic spectrum? Do you guys have any ideas? Heat forms part of the electromagnetic spectrum, not math. So, cosmic rays are subatomic particles traveling. Urine forms part of the electromagnetic spectrum. Neutrino experiment is one of them. But let me show you where this is leading up to. So cosmic rays are subatomic particles traveling through space at tremendous velocities. Almost no cosmic rays reach the ground, but some of them smash into gas atoms in Earth's upper atmosphere, and fragments of those atoms shower down to the ground. Those secondary cosmic rays are passing through you as you read the sentence. Other types of particles from space interact weakly and seldom with Earth's atoms. So huge detectors must be built to catch and count them. Detectors for some kinds of cosmic rays have been carried on balloons or launched into orbit, while others have been built deep underground. So, do you guys recognize this facility? Yes, that is LIGO. So what LIGO does is, let's go back to these. We have a tunnel going this way, a tunnel going that way. These tunnels are basically almost a kilometer long. So what it does is we have a single laser that we have a laser over here and a mirror and a mirror. So the laser goes down this tunnel, hits a mirror, reflects back. Go down to this mirror, reflects back. So what happens? How does it work? So when a gravitational wave moves through these detectors, the image we receive here will be different because of the gravitational move before here. The time for this laser to reflect back and the time for this laser to reflect back will be different. So a gravitational wave affects the interferometer's arms differently. When one extends, the other contracts, as they are passed by the peaks and troughs of the gravitational wave. So normally the light returns unchanged to the beam splitting from both arms, and light waves conceal each other's output. So here we can see how it works. So here we can see if these two, if nothing detects, they just cancel each other out. But if we see an image here, that means a gravitational wave has moved through the area and we have detected gravitational waves. But what causes gravitational waves? Gravitational waves can only be detected if we have objects of immense mass basically knocking into one another, and that produces a ripple in our space-time and we can see it. So here we can see, for example, two black holes knocking against each other. Two neutron stars can do the same effect. And that will cause gravitational waves, and we can pick it up by using instrumentation such as LIGO. And that, ladies and gentlemen, is tonight's lecture. Any questions?
Yes, sir, I have a question, sir.
Yes, go ahead.
So what happens to dead stars? So like for example, your you just mentioned your neutron star. So like once it cools down, like what happens to it? Does it stay a big structure but you can't see it, or does it like disintegrate?
So we can discuss the death of stars thoroughly in this course. So it all depends on the size of the star we are dealing with. So usually a neutron star is a star that is very big, that went supernova. So usually when it's above a certain mass, it implodes on itself and forms a black hole. But if it's not at that critical mass, it will form a neutron star. Then we get different neutron stars. So the most common neutron star is called a pulsar. So it will have on a piece of its surface still radiates a little bit of energy, and when it spins around, it looks like a lighthouse. And we can detect those pulses. That's why we call it a pulsar. And that will continue flashing pulses until that radiation is finished, and it will just be a big chunk of mass or big rock in space drifting around, if you want to put it that way.
So and we won't be able to detect it in any way.
Yes, we can detect it while it's still radiating energy. And we can still detect it by looking at its gravitational pull.
Okay, thank you, sir.
Yeah, it's a pleasure. How do we draw landmarks in the dark? So that's why you have to draw your landmarks beforehand. You need to know where your landmarks is. So, but how will you know where the moon is going to be? That's part of the research. So the website link I posted to you will show you the angle at which it will be from the east. You can start at any day of the month, but just look carefully at when the moon is rising, when the moon is setting. Find a time that is comfortable for you. But that is why I suggest starting on the 20th or 21st of this month. It's no problem. You're more than welcome to ask questions. That's why I'm here. It's a pleasure. So if you guys have no further questions, you're more than welcome to log off. I will see you all tomorrow night. I'll remain active for 1 or 2 more minutes for if you have something you want to discuss or have a question. I'm glad you guys enjoyed the lecture. I'm also going to log off now. Have a wonderful evening and see you all tomorrow night.